So today we're pleased to have Prof. Amare Abebe from Northwest University. So Amare completed his BSc in Physics and Mathematics at Addis Ababa University in 2006, and he did his MSc and PhD, finishing in 2013, in Cosmology at the University of Cape Town. He has been at the Physics Department and Center for Space Research of the Northwest University since 2014, and he is there now Professor of Physics. Also the current Junior Focus Area Coordinator for Mathematical Physics at the Center of Excellence. And his professional memberships also include the National Institute for Theoretical and Computational Sciences, the South African Institute of Physics, the South African Mathematical Society, the African Astronomical Society, and the International Astronomical Union. So today, Amare is going to talk to us about shear-free perturbations of the dark universe. So you can go ahead, Amare.
Right. So these shear-free perturbations that I would like to talk about today will be based on a brief introduction to theories of gravity in general and the cosmology, the Concordance Cosmology that's based on, one of the standard theories of gravitation that we have, which is general relativity. And then I will talk about the shortcomings of the Concordance model and briefly discuss about new frontiers in the form of alternatives to gravitation and cosmology. And one of the alternatives that I will be talking about would be FFR theory of gravitation, and another one is something in the form of a dark cosmological fluid, specifically the Chaplygin gas fluid, and the cosmology based on that fluid. And I will talk about the main theme of this presentation, which is shear-free perturbations and the kind of solutions one gets if we assume a modified gravitation, specifically the FFR theory, and the dark fluid phenomenology, which is the Chaplygin gas cosmology. And I'll then summarize my work and suggest some future outlook. Right. So to start with, I think by now we all know that there is some recent dilemma in the cosmological and astronomical cosmology community, rather, which is the recent discovery of the accelerated rate of expansion that has resulted in a number of new theories in the nature of gravitational physics and cosmology that have resulted. And this involves new alternatives or generalizations to the theory of gravity itself, one of which is the FFR gravity, and another of which that I'll mainly focus on will be the dark fluid models, among them the Chaplygin gas model. And so the main focus in this work is basically to understand the dynamics of the linear fluid flows, because this is important to understand the relationship between Newtonian and relativistic GR limits of this flows. And this is specifically relevant both in the physics of gravitational collapse and the late time states of cosmic structure formation. And these cosmological fluid flows that I'll be talking about are described by differential properties of time-like geodesics, such as the expansion, the shear, the rotation, and the acceleration of the velocity field of the cosmic fluid. Now, if we have these modifications introduced to our cosmological field equations, it's important to make a consistency analysis of the field equations for different models where certain integrability conditions will arise as a result of imposing certain restrictions to the field equation, such as, for example, the shear-free condition, which we are going to introduce. So if we introduce shear-free conditions to the fluid flows, are there some yes, there are certain conditions that will arise, but those conditions should be constrained, and the kind of constraining that I'm going to do in this presentation is not the observational constraint that one can do using astronomical and cosmological data, but theoretically, what kind of inconsistencies will arise, and how do we deal with those inconsistencies to come up with a self-consistent set of equations that describe the cosmological evolution and the time structure formation. Okay, so now I want to first talk about gravity because it's important in the general scheme of things. We all know that there are four fundamental forces in nature. We have the strong, the electromagnetic rather, the weak, and the gravitational interactions. All of them playing their role in their own range of applicability. Whereas we know that the strong and the weak interactions are interactions that are effective in extremely short range, like in the subatomic scales. We have the electromagnetic interactions that can also influence things on infinite distance range, like gravitation, but overall the universe is more or less neutral, and that is also ruled out from playing a big role in the overall dynamics of the universe. So that leaves gravity as the most important, the weakest, but the most important factor in the cosmological dynamics. And that's why we focus mainly on the gravitational interaction and the effect it will have on cosmological evolution. But then what is gravity? So it depends on who you ask. If you ask Newton a couple of centuries back, he'll tell you that some sort of fictitious force field that exists between two massive bodies, and that it is inversely proportional to the separation between the bodies and directly proportional to the masses themselves, right? But when it comes to the Einsteinian interpretation, gravity is nothing but the curvature produced by the presence of massive bodies around an otherwise flat space-time. So based on this, we can say that the modern interpretation of gravity is nothing but curvature, space-time curvature. But then when it comes to space-time curvature, there are three possible representations for that. One of which resulted in the Einsteinian picture of general relativity, and two other of which are currently being actively sought after the gravitational community because of this new phenomenology that resulted in the need for new theories of gravitation. So briefly, I'll tell you that the three representations will be the one represented by the Riemann Tensor, which basically shows us the failure of the these parallel transported vectors along a closed curve coming back to the original orientation. So the rotation of a vector transport along a closed curve is what is usually represented by the curvature, and that results in the general theory of relativity. And then we have also this other representation that gives us this so-called torsion, which gives us the non-closure of parallelograms formed when two vectors are transported along each other. And this has resulted in a theory of gravity that is known as the teleparallel equivalent of general relativity. And the third and recently fashionable, more or less, interpretation of gravity is the so-called non-metricity, and the cosmology based on it, which is refers to as the symmetric teleparallel equivalence of general relativity. This is basically the variation of the length of a vector as it is transported along the curve, and that results in this non-vanishing of the divergence of the metric, the covariant divergence of the metric tensor in general relativity is assumed to be 0, but in this case we have a non-vanishing divergence. And as a result of this, we have this other formulation of gravitational theories based on the curvature interpretation. So
Amare,
as a result of this,
if I may
yes.
ask a question. So, I thought about the previous slide. So in GR, we can always choose the connection so that we can get the covariant derivative of the metric to vanish. So is it that in this theory, we're not allowed to make that choice? Like there is no connection?
That's basically what this non-metricity story is all about, I think. Yeah.
Okay.
Yeah. So based on these three possible interpretations, we then have three possible gravitational formulations, as I said in the previous slide as well. So in the GR interpretation of curvature, we have the action given in terms of the Ricci scalar R. When it comes to the teleparallel equivalent of general relativity, we have the action given in terms of the torsion scalar T that we see here. And in terms of the non-metricity, we have the action given by this non-metricity scalar Q. And recently, because of that accelerated expansion story that I mentioned, we have this. So the idea so far had been that these three formulations of general relativity, the symmetric teleparallel equivalent and the teleparallel equivalent theories of general relativity were assumed to be, describing exactly the same background expansion, and people had just focused on the GR, since the other ones are equivalent formulations and they describe the same background cosmological elements. But because of the recent story, then there has been modifications of general relativity into something called f of R, where you generalize your action to a function of R rather than just R or its linear dependence. And then there is also an equivalent generalization of the torsion gravity into f of t, and the non-metricity has now been generalized into an f of q. So although these three theories at the background level in their original forms describe the same dynamics, it's thought that when you generalize them into an f of r or f of q or f of t, the three different versions of gravitation do not necessarily describe the same background dynamics. Right. So the concordance cosmology, which is based on the Einsteinian description of curvature and hence general relativity, is given by this kind of action here, where you have the Ricci scalar, as I mentioned earlier, and then of course one has to include matter, and there's this recent, not really recent, but this afterthought of Einstein's original theory, which is called the cosmological concept, that has been introduced to this action to describe late-time cosmology. But initially it was introduced for something completely the opposite, which is Einstein had thought that when his field equations described an expanding universe, he wanted a static universe because at the time the universe was assumed to be static 100 years ago. And then he added this cosmological constant to produce that kind of static universe, but it was later discarded because of the observational evidence that the universe was expanding. But it will reappear, as I'll talk about it in a moment. So these Einstein field equations given by equation 1.1 are actually a system of 10 coupled linear hyperbolic elliptic partial differential equations. So, and they are second order, and these are, as you can imagine, extremely difficult to solve analytically. So they have been only a few exact solutions without, extreme assumptions of symmetry and other considerations. So even the most powerful computers have not been able to solve the 10 equations in their entirety without making certain assumptions in the equations and the nature of the universe itself. So the other two descriptions that I mentioned are just thought to describe the same background expansion history if we make this kind of choices to the torsion and the non-metricity scalar in terms of the Hubble parameter that I will describe in a moment as well. So the Einstein field equations predict an expanding universe, namely if you have the size of the universe at a given time compared to the same to the size of the universe at some later time t, you will see that as time progresses, the universe is getting bigger and bigger in size, which can be, the analogy here is I'm trying to give here is that if you have two galaxies in space-time and in space, and you measure their distances, you'll see that over time the two galaxies are farther away from each other, and this applies to any given, on average, any two galaxies in the universe, and that can only mean that the universe itself is expanding. Right. So the evolution of the energy density of the universe can be given in this kind of equation, which together with a certain choice of the relationship between the energy density mu and pressure P will give you the how the energy densities over time will evolve. And you'll see that in terms of the scale factor here, as the universe expands, the energy density of dust-like matter, which I described as mu d here, scales as 1 over the scale factor cubed. And for radiation, you have the energy density evolving as 1 over the scale factor to the power of 4, whereas the energy density of the cosmological constant that I mentioned previously remains the constant in most considerations, although there's also this running cosmological constant story in its own right that needs consideration as well, which has gained recent attention. So based on the amount of matter and energy we have in the universe, we can have what we call a closed universe, which is represented by this top figure here in the form of a spherical distribution. Or we can have a saddle-like structure where the energy density is below a certain critical density, and the one where the total amount of energy in the universe is equal to a certain critical density is represented by this flat space. Yeah, and depending on whether the actual universe is flat, open or closed, the scale factor and hence the expansion of the universe will be represented by this figure in the right pane of this, where you see that if the universe is closed, where k is positive, you have a universe that starts singularity, call it the Big Bang, expands to a certain maximum size and contracts into another singularity, which we refer to as a big crunch. The universe is flat, represented by the k equals 0 in the figure. You have a universe that expands forever, but approaching a certain asymptotic size in the far future. Whereas if you have a universe that's open, represented by the k equals less than 0 curve here, you have a universe that expands at an ever accelerating rate, and it might result in what's sometimes referred to as a thermodynamic heat death, or space-time itself will rip itself apart and results in some sort of empty universe scenario. Right. So, as I said earlier, the prevailing understanding at the time of the derivation of the Einstein field equations was that the universe was static. So, Einstein had included this so-called cosmological constant to describe the to balance the right hand and the left hand side of the equations in such a way that you would get static universe. But since observations in the 1920s confirmed that the universe was expanding, we had abandoned the cosmological constant for a very long time, apart from certain theoretical considerations now and then. And it was only in the late 1990s that this cosmological constant was introduced as an alternative to describe the accelerated expansion. So what is referred to as the dark energy component of the universe. But the problem with this simple fix to the cosmological evolution by adding the cosmological constant is that there is something called the cosmological constant problem, which is 120 orders of magnitude discrepancy between two numerical predictions for the value of the cosmological constant itself. So the value that's needed for an accelerated universe and the one that's predicted from quantum field theories, their values are extremely different, about 120 orders of magnitude different, and that's it's usually referred to as the biggest discrepancy in any branch of science. So because of that, the cosmological constant is in some circles frowned upon as a solution to the dark energy problem. But anyway, the main problem is that if we have no cosmological constant or no other form of matter or energy introduced to the field equations, one of the equations that specifically deals with the accelerated expansion of the universe is given by this equation here, 1.2, which for any positive energy density and pressure, you would always have this term inside the brackets always positive. And because of that, your A double dot, which describes the acceleration of the expansion, will remain negative. And there is no way of reconciling that with observation that A double dot at the present moment is actually positive. That's why people thought there must be some sort of term that should be put on the right-hand side of this equation. And that happens to be the cosmological constant, being the simplest alternative there, such that if the cosmological constant that is in 1.3 is bigger than all the terms on the to the left of it, then there's a chance for A double dot to be positive. By the way, A is always positive because it's just the scaling of the size of the universe, so it cannot be negative by definition. That's why we need this. The other possibility is if, of course, this energy density plus 3p, the rho plus 3p term is negative somehow, and that is where the dark fluid phenomenology that I'll describe in the second part of my talk will focus on. If that term is negative without even modifying the theory of gravity, you somehow have some sort of exotic fluid with that property. You can also have an accelerated expansion without modifying the theory or without adding the cosmological constant. So based on the standard theory of gravity with general relativity, our current understanding of cosmology is that it's a four-dimensional homogeneous and isotropic spacetime that started off in the form of a Big Bang about 13.8 billion years ago. And by a homogeneous, we mean that all regions of the space will look alike. There are no preferred positions there. And by isotropic, we mean that there are no preferred directions. If you are an observer somewhere in this in the universe, then there is actually no preferred direction. You can look in any possible direction, and on average and on very large scales, the overall distribution of structures looks the same. So that's basically what we have in our understanding of the universe today. But of course, there are shortcomings, as I mentioned, although the Big Bang theory is by far the most successful theory so far in predicting like expansion of the space and the origin of the fossils for the Big Bang is usually referred to as the cosmic background radiation. They are, the afterglow of the Big Bang from about 380,000 years after the Big Bang. And we also can explain the formation of the primordial elements, and we can explain the abundance of these elements in the universe and so forth. And we can also describe the galactic evolution distribution using the standard Big Bang theory. But then there are two serious puzzles that remain unanswered in that standard cosmology, in the form of early universe problems, which have to do with the so-called horizon flatness and homogeneity problems, and there's also this so-called magnetic monopole problem. That are issues that arise when one considers standard cosmology in the early epochs of its evolution. And then we have this so-called late time or large-scale problems, namely the rotational curves of galaxies and the formation of large-scale structure cannot be explained without some sort of matter that we have not seen so far, but it's filled gravitationally. And then there's other cosmic acceleration problems that I mentioned, form of a cosmological constant or dark energy. So based on this, our current estimate of the energy budget of the universe involves a 68% of that going into some sort of energy that would be needed to accelerate the universe at late times, and about a 27% of that being an invisible form of matter in the form of a dark matter. And then only 5%, about 5% of that would be what is needed to form all the structures that we see in our cosmic neighborhood, for example, the stars and galaxies and humans. Everything that we see composed of baryonic form of matter is from about 5% of all the total energy budget of the universe. And that's basically implying that we live in a universe about 95% of it, which is unknown, the dark stuff. Right. So what are the new alternatives? So, for example, this I mentioned are solved through an early epoch of cosmic acceleration called inflation. That seems to be the standard recipe at the moment to describe why, for example, we don't have magnetic monopoles in the universe so far discovered. Why why we still have structures in the universe, although we started off with an extremely homogeneous distribution of the space-time structure and things like why do we have a universe that's almost flat at the present time, although in the early universe that curvature could have been different from the kind of flatness that we have today and so forth. So that is one of the paradigms at the moment, but of course there are several other alternatives to inflation as well. And then for the late time cosmology, there are certain considerations such as considering inhomogeneous cosmological models or anisotropic cosmologies, relaxing the homogeneous and isotropic assumption basically, and maybe changing the fundamental constants. Like, what if the cosmological constant is not a constant? What if all the other constants, such as the speed of light, the gravitational constant, and other usually assumed constants are not really constants, but evolve with the evolution of the universe itself? That's one of the active areas of research as well. And some other models include those cyclic cosmological scenarios. We have a universe that starts off as a Big Bang and it's in a big crunch and starts off as another Big Bang, and we have these different iterations of realizations. And our current universe could be one of those realizations that might have inherited some of initial conditions from a pre-existing universe, and so forth. The other and main proposal is to see if GR itself is incomplete. If we assume GR is incomplete, there are several possible ways of extending or filling the gap by either introducing extra fields to the matter content of the universe, or by increasing or decreasing the dimensions of the universe. Like, for example, it mostly involves having extra dimensions, like 5-dimensional universes, or in the case of string theory, even higher dimensional universes. Might suggest that some of the hidden properties of the universe could be hiding somewhere in another extra dimension, and that's why we don't see it. In some of those cases, for example, the suggestion is that the current expansion could be that gravity could be getting weaker over time, because the universe is leaking it into its extra dimensions and so forth. So there are all these considerations. Another possibility is, earlier I said that GR is a second-order theory, but what if we have higher order theories, like fourth-order theories in the case of FOFA? Could this, in that case, for example, a second-order theory has, a solution to a second-order differential equation can have less conditions to be imposed than the one of the fourth-order theory, in the form of boundary conditions, initial conditions. Because of this, the people think that having a higher order theory could have more freedom to play within the field equation than a second-order theory. Based on this, you see that there's a large number of modified theories of gravity. The purple highlighted ones are the ones that I have been myself involved in dealing with certain aspects or another of those theories. But you'll see that we have all this, large pool of consideration to choose from if we think that GR is not the standard theory that describes our universe in its entirety. But we know that GR works very well for example, in astrophysical scales. For example, description of black holes and astrophysical systems and so forth. There seem to be no big problem there. So I'll just briefly take you through these slides very quickly. Actually, I'm not going to talk about the details of these equations, but the point is that if we have this kind of background formulations, one can make it in the form of describing the background geometry in terms of the Einstein curvature tensor, the Ricci tensor, and the Ricci scalar, and the metric tensor, and so forth. But like I said, I'm not going to dwell on this one much more than that. And we also have the matter content of the universe described by the energy momentum tensor here, where the mu and u and p and all those are defining the energy momentum, the energy density, the four velocity vector field, the pressure, isotropic pressure specifically, the projection of the metric tensor on the spatial sections, the heat flux of the universe, and the anisotropic pressure, and so forth. And we'll talk about these time derivatives and spatial derivatives defined in this formulation in terms of the four velocity vector field and the projection tensor that I showed you here. But if you need more details on this, and if you have any specific questions, that's why I put these slides here, not more than that. I'll talk about divergence and curls of vectors and tensors. I mean, they are defined in this specific manner, for example. So we have the four velocity vector, the divergence of that vector given in terms of the acceleration, the expansion, the shear, and the vorticity terms that I kind of mentioned at the beginning that are defined in these ways. And we also talk about the electric and gravity, the electric and magnetic components of Weyl tensor defined in this specific form from the Weyl conformal curvature tensor, which is defined in terms of the Riemann tensor, the metric tensor, the Ricci tensor, and the Ricci scalar. These quantities, which will play a somewhat big role in my next slides, are defined as the gravitoelectric or to the Weyl tensor, which in Newtonian analogy will describe a free gravitational field or tidal forces, whereas the gravitomagnetic component of the Weyl tensor, the H alpha beta, is responsible for gravitational waves. So any space-time with propagating gravitational waves necessarily should have this H alpha beta quantity in there. And as a result, because there are no gravitational waves predicted from Newtonian gravitation, we actually don't have a Newtonian analogy to this H alpha beta term there. So when I have a vanishing quantity for H alpha beta, I will refer to that a quasi-Newtonian formulation and so forth. So, whereas if the E alpha beta, the gravitoelectric component, is vanishing in a certain spacetime, I refer to it as an anti-Newtonian spacetime. I will also base my discussions on this assumption that any quantity that vanishes in the background is first order or linear perturbation to that background by virtue of this so-called Stewart-Walker. So just to give you a brief description of these F of R theories, they are a subclass of the so-called fourth order theories, because there are more fourth order theories than just F of R. They are introduced by adding a generic function of the Ricci scalar to the action, and I have not intentionally included the cosmological constant here, as that I did at the beginning, equation 1.1, because what we want is to remove the cosmological constant from playing the role of dark energy, and instead have that dark energy come from this modification of the theory in the form of the F of R. And as a result, the field equations would be generalized to this one here, where the blue highlighted terms are the extra terms that will come as a result of the modification. In GR, you just have had this G alpha beta equals T alpha beta term. So everything else will be coming from the modification. These are fourth order theories because of the highest order of the derivatives in the field equations. And these are usually considered to be the simplest generalization to the Einstein's general relativity, and they come with an extra degree of freedom that could be playing the role of this extra field, matter field, or a dark energy field that one needs to explain cosmic evolution properly. In terms of cosmological viability, there are attempts to constrain these models using observational data, of course, just like GR. This other theories should pass the test of observation. If they fail observation, then they're basically not good theories. That's the point. The other possibility is, of course, to follow the theoretical avenue of constraining these models and see if there is some internal inconsistency that arises by considering generalized models. And this is a kind of thing that I want to show you guys. So the extra terms that come as a result of introducing a modified theory in the form of F of R, we have extra terms that contribute to the energy density, to the pressure, to the heat flux, and the anisotropic pressure of the fluid by introducing a more general theory. So all the blue terms here would be zero in GR. So you have them here for free if you modify the theory without introducing an extra dark energy or dark matter field, basically, that describe that. And the total energy density, pressure, heat flux, and anisotropic pressure in the universe can now be described by the one that we have for standard matter distributions plus the extra terms that come from so-called curvature fluid. We refer to this as the thermodynamic components of the curvature fluid. And then we have this so-called Bianchi and Ricci identity that give us the decomposition of and hence the evolution of the different thermodynamical evolutions that give us the evolution of the energy density over time given by this equation, the one for the curvature fluid given by this second equation. The theta here is the volume expansion of the universe. The Q is the heat flux of the fluid in the space-time and so forth. And all of these have their own evolution equations that are telling us how these quantities are evolving over time, but they need to be constrained in such a way that they are evolving consistently on any future or past hypersurface as well as not just at any given time. So these are our constraint equations there. So that covers a brief introduction to the modification of gravity. But if I want to keep the general theory, but instead include an extra exotic fluid to the Einstein field equations of general relativity, then introducing one of those dark fluid models called the Chaplygin gas gives us a negative pressure that's needed for the dark energy. The interesting part about this model is that it has a dark energy component with a constant A here, and it also has another component that evolves as a constant divided by the scale factor to the power of 3 that I mentioned earlier is the evolution of the energy density of dust. Because of this, it has an early universe dark matter-like property and late time dark energy-like property that can solve both the dark energy and dark matter problem in one go, basically. So these have been widely explored at the background level, but so far they have not been really dealt with in detail in at the perturbation level, and that's why I want to introduce these things. So in the shear-free scenario, there have been a number of interesting work that have shown that if you have a universe that is dominated by dark dust-like matter or any perfect fluid matter for that matter, then such a universe cannot expand and rotate at the same time. And if provided that the shear of the space-time is set to 0. So any shear-free universe with perfect fluid matter in it, avoids this condition of simultaneously expanding and rotating. And this has been shown by a number of works starting from the 1950s all the way to as recently as, about a decade ago. And what we did in one of our works in the shear-free perturbations of modified theories of gravity is that if you have a theory of gravity described by the f of r gravitation, the GR result, which would avoid that simultaneous expansion and rotation, can be avoided provided that this equation 3.1 is satisfied. And that blue highlighted term inside the brackets is actually the extra term that gives you that kind of freedom. So even if theta times omega alpha, which is expansion times the vorticity is 0, provided that other term is non-zero, provided that other term in the bracket is 0, then you have simultaneously expanding and rotating universe. So this is one of those interesting results you get if you have a modified theory of gravity. So I'm not dealing in detail about this, but the main point is that you can have such universes governed by f of r theory of gravitation that you would get, but that you would not get in the standard general relativistic limit.
Amare,
if you want,
so
yes.
is this shear something that can be observed potentially, like cosmologically, or is there any indication of this shear, like the universe expanding and also kind of rotating?
Yeah,
or is it just theoretical at this
one
point?
of the things. Yeah, so yeah, I'm doing this from a purely theoretical point of view, but the hope is that at some point, if there is this discovery that the universe is in fact rotating and expanding at the same time, then GR would not be able to describe that and would resort to a more general theory like F of R. That's the hope, basically. So yes, another thing that we want to talk about is this class of non-rotating fluid models that are described by F of R theory, but not described by GR because of the background inconsistency and so forth. And I also want to briefly talk about these so-called quasi-Newtonian models, where we have a dust-like fluid with vanishing gravito-magnetic components. And if you have this kind of space-time, you can have a consistently evolving a universe, provided that these equations are satisfied. And such universe have been described both as the GR limit and F of R limit. And the idea is here is that if you consider this model and including the anti-Newtonian universes, there are certain instabilities when one considers the GR limit. But if you have properly evolving and consistently constrained background universes that satisfy these equations that I have written down here, for example, such universes can exist. For example, anti-Newtonian universes in GR have been shown to not exist. But in GR, if you have that 3.8, equation 3.8, you can have an anti-Newtonian solution. So this is just to show you that even if you have certain limitation to the GR prediction, you can have that by relaxing the theory of gravity, such as a simultaneously rotating and expanding universe. The GR doesn't want to allow that. F of R can allow it. And using maybe future data that show such universe existing, we can differentiate between theories and have one of those theories that predict correctly being the preferred theory of that time. The other thing I want to briefly talk about is Chaplygin cosmology, which is, as I said, acting like a dark matter and dark energy at different epochs of cosmic evolution. So if we want to consider such a universe, and I want to consider the total energy density of the universe as being the sum of the dust-like and Chaplygin gas-like fluids, the total pressure is now coming from the Chaplygin gas because the pressure of matter is 0, and the heat flux can be described in terms of the heat flux due to dust-like matter and the Chaplygin gas fluid. And I'm going to consider a peculiar velocity between the Chaplygin gas model and the 4-velocity vector of the total matter, and hence write the heat flux due to the Chaplygin gas as described by this term here. And I'm going to consider this to be a non-relativistic correction approximation. And using that, these blue highlighted terms are the ones that are modified due to the introduction of this Chaplygin gas in the field equation. So the top class of equations is our evolution equation constrained by this lower class of equations by describing the constraints thereof. And one of the things that we want to consider is that if the shear is present, you have this equation given here. But if you turn off the shear, this equation becomes a new constraint where if the heat flux for the Chaplygin gas is turned off, then you get the evolution of this equation given by another constraint given by 3.25. So this solution has actually been shown in one of our recent papers to have a simultaneously expanding and rotating scenario. So even the Chaplygin gas model, the shear-free limit can have a specific solution, not in general solution for all possible scenarios, but very restrictive solution given by this equation actually, where we showed that if provided that these equations are satisfied, we can have an expanding and rotating universe scenario as well for the Chaplygin gas model.
Amare, when you say solution,
yeah.
When you say solution, do you mean a specific metric, just like we say Schwarzschild solution, or Is it like an analytic solution or numerical? Maybe I didn't get that.
All right, I'm not referring to the metric. So I'm assuming that the metric describing the universe is actually the FLRW metric, right?
Oh, okay, so you still have FRW.
Yeah, yeah, you still have FRW, but the thermodynamic properties and the expansion and rotation properties, that kind of space-time show different properties. So that's what I mean by, you can call them maybe conditions of the expansion and the rotation and so forth. Yeah.
Okay. By the way, we are at 20 past, so I think, yeah, I mean, to give a little bit of time for questions, maybe you can slowly summarize.
Yeah. All right. Yeah. So I just want to quickly summarize this. So if we have irrotational fluids, like when the vorticity is 0 for this shear-free solutions in the Chaplygin gas phenomenology, then we can actually get we had this equation before. The 4-velocity vector can be given in terms of the Chaplygin gas pressure and the total pressure and energy density of the Chaplygin, the sum of these two. And because of this condition, if we have an irrotational, if the curl of the gradient of the vector is 0, then that vector is irrotational, and that vector can be written in terms of the gradient of some scalar field. And that scalar can be given in terms of the energy density and the defining parameter of the Chaplygin gas field itself. And if we take that to a quasi-Newtonian scenario where the H alpha beta turned off, then you can actually see that although they are unstable for the GR scenario with no Chaplygin gas and so forth, but such solutions can have properly behaving background solutions if you have a Chaplygin gas component in it. And one of the conditions that you get is that the heat flux itself can be given in terms of this scalar field that comes as a result of the irrotational nature of the fluid itself. And by combining some of the equations that I mentioned earlier, you can actually write that scalar to be described in terms of the expansion and some partially constant quantities. And from that, you can write the 4 velocity, the 4 peculiar velocities that I mentioned to be written in terms of either the expansion scale or the energy density. And you can also calculate the 4 acceleration of such a universe in terms of those quantities as well. In the case of the anti-Newtonian scenario, these are also extreme cases where the electromagnetic component of the gravito-electric component of the Riemann tensor is 0, and these are the farthest from the Newtonian analogy, and such universe in the GR scenario, as I said earlier, do not exist, but we have shown that if you introduce a Chaplygin gas fluid in the space-time behaving in a particular way, moving at some peculiar velocity with respect to the background total fluid, you can have those solutions provided that those conditions are satisfied. One of those conditions is that the heat flux is given in terms of this quantity there, and comparing this with this equation 3.44 actually, then this new constraint for the shear, namely that it has to be a divergence-free shear, can describe a properly evolving linearized perturbed universe. So to summarize, our understanding of gravity has evolved over time, and there are 3 possible descriptions of gravity that give equivalent cosmic evolution. In terms of GR, we have the curvature. In terms of the teleparallel equivalent theory of general relativity, we have the torsion, and in terms of the symmetric teleparallel equivalent theory of gravity, we have the non-metricity playing the role of that Newtonian fictitious force field analogy. without the generalizations into f of r, f of t, and f of q, as I said, we have all those three possible interpretations giving similar background expansion history. But if we modify them, then there is this possibility people are exploring that they can explain away the dark energy and dark matter scenarios. And due to the higher order corrections in the f of r theories, as I mentioned, there are some interesting cosmological solutions that do not exist in GR, such as, for example, the simultaneously rotating and expanding solutions, the quasi-Newtonian solutions, and the anti-Newtonian solutions that are well defined if you deviate from the GR restrictions. And we have shown that similar descriptions can be provided through a Chaplygin gas model that has a dark energy, dark matter property at different epochs of evolution. Possible new frontiers, I think the analysis of these density and velocity perturbations can give us some insight into the nature of structure formation that compared to the ones predicted by pure GR with standard matter, and dark energy scenarios can give us some clue about whether these theories are viable or not. And of course, I only talked about perturbations to linear order and generalizing these solutions to non-linear orders, although they will be much more complex, could give us some more insight into whether these theories are worth pursuing further or not. And more generalized, realistic f of r and Chaplygin gas models can also be constrained using this sort of theoretical analysis, because I only use the simplest possible models for these generalizations for our initial analysis. And then, of course, observational constraints are the most powerful, because if something is observed and does not fit with your data or contradicts with your theory or contradicts your theory, then that theory is automatically ruled out. And that's one of the best things to do. And these are left for future exploration from my side. Right, I think that's it.
All right, thanks, Amare, for the nice talk. Let's everybody thank Amare. And maybe we are running a little bit late on time, but let me ask if there's any questions from Zoom first. You can unmute if you have a question for Amare. Okay, maybe I can ask a question in the meantime, Amare. So you mentioned that, I think that you mentioned in one slide that this Chaplygin gas model can simulate an f of r model. Did you say something like that, that you can potentially
yes,
not be sure which one you have, or is there a way to really distinguish between observation?
Yes, so in one of the works that we did, let me see where I mentioned that. In one of the works that we did, we actually said, okay, we have this background expansion described by the f of r model, and we have this also by the Chaplygin gas, but there are certain concerns about the nature of the Chaplygin gas, namely that it's not one of those fluid models that we have in nature that we haven't seen so far. So we say, okay, what if with this Chaplygin gas is some manifestation of the deviation of the theory of gravity from general relativity itself? And we created the f of r field equations to the Chaplygin gas equation, and we solved the form of the f of r that can describe potentially not replace the Chaplygin gas, but is some geometric modification of the theory rather than an exotic fluid. Yes.
Okay, but that's at the background level, I imagine, right?
Yes, that's purely background. Yes, that's correct.
Okay. And actually, that brings me to another question I had, that if you have f of r, I assume that also changes the equation of motion for gravitational waves. Like if you just think of fluctuations of the background, is that significant, or is it more or less unobservable?
I haven't done anything of that sort myself, but from what I have read, they said that FOFA predicted the amplitudes of the gravitational wave predicted by FOFA within the observational limits that people have found in the recent discoveries of for example, the gravitational relativities to the black hole merger. So those the theories have not been ruled out by the discovery of the gravitational waves. Yeah.
Okay, cool. Thanks again for this presentation, and it's very exciting to see how this is going to go. As we learn more, I guess, about the universe, some of these things are going to be ruled out or supported. I guess possibly quite soon, right?
Yeah. There's more and more data coming, so we should be able to once and for all rule out some of those theories or continue working on them. Yeah.
Actually, what would be the main? Would it be like CMB, like better CMB kind of measurements of the CMB kind of modes, or would it be like galactic stuff like dark matter curves, or like what is the main constraint on these models you're discussing?
Yeah, I think. Yeah, so it looks like so far that we have not been able to differentiate between the background expansion history and in terms of GR and the modified theories, especially FOFI. I mean, there have been a number of those theories that have been rolled out already. So my main focus, for example, is to look at more at the level of the perturbations. Mm-hmm. So the CMB data from the CMB, the power spectrum, the matter power spectrum, and those kind of analysis, I'm hoping can give us more insight into this. Yeah.
Okay. Thanks so much, and see you around. Bye.
All right. Thanks a lot, and thanks for Laura and Ed for inviting me to give the talk.